Okay, this is going to be our fourth video in our electric charge and electric fields series here. In this video, we are going to be interested in calculating the electric field for some charge distribution, right? So in the previous video, we were interested in calculating the electric field around a point charge. Now we're going to be dealing with, we're going to start off by dealing with several point charges, calculating the electric field around those, and then moving on to calculating the electric field of sort of macroscopic charged objects, so charged rods, charged rings, charged disks, so forth, right? So originally I was going to do this all in one shot here, but there's quite a bit to sort of go over, and I'm going to break it up into a couple of videos. We're going to take a look at the electric field of several point charges, and then we're going to jump it up to sort of continuous charge distributions, where we're going to have to include ideas like charge density and introduce some integral calculus. So I'm going to introduce all those ideas, but I won't actually do the sort of full-blown problems that involve integration in this video. I'll save that for the next one. Okay, so let's get started here. We've seen already that we can calculate the electric field for some point, right? Using the equation that we see here, equation 1. We've also seen that the principle of superposition allows us to write the total force experienced by our test charge as the sum of individual forces resulting from each of the charges, right? And so we saw this a couple of videos back. I don't remember exactly which one it was, but we saw that we could add up, if we had, let's say we had three charges in a problem, we could add up the influence on the third charge from charges 1 and 2 and get the total force experienced by that third charge, right? And that's basically what we're writing here in equations 2 and 3. And so we can combine these two ideas, and if we do that, we end up with this sort of expression that we see here in equations 4 and 5, where we combine these ideas, and we can now write down the electric field at a point, the total electric field at that point, as the sum of the contributions from a number of different point charges. So let's say we had, 3, 5, however many point charges we wanted, and we wanted to calculate the electric field at some other point P. Well, we could do that by calculating the electric field contribution from our first point charge, then from our second point charge, and so on, until we did all the point charges, and then add them all up, and that would give us our total electric field at that point. Okay. So we can think of this as sort of our net electric field, but in the end, really this is just the electric field at that point, and it comes from the sum of all these individual sort of contributions. Okay. So at this point, we're gonna basically make use of this idea and do an example with still discrete points, right? So in this next example, which is directly from the textbook, which is 21.8, we're going to look at this dipole here. So we have a positive charge and a negative charge separated by what looks like 10 centimeters here, and then we're looking at what the electric field looks like at points A, B, and C, right? So in this example, we're going to be looking at discrete, still discrete point charges, but as we move on, as I mentioned, we're going to have to start looking at charge distributions, where we have, some sort of macroscopic object, whatever it may be, a rod, whatever, and we're going to have to look at the electric field around that object. But we'll start off with this. So let's get right into the example here. So we have 2 point charges, Q1 and Q2. They have charges of 12 nanocoulombs and minus 12 nanocoulombs on them. They're separated by 10 centimeters, as we said before, so 0.1 meters. Okay, it tells us that these are called electric dipoles, so such pairs of point charges with equal magnitude and opposite sign are called dipoles. And then we're going to want to compute the electric field caused by Q1, the field caused by Q2, and the total electric field at points A, B, and C. Okay, and so this is an interesting problem because of the sort of symmetries that we can make use of here, right? So because we're looking for points that lie on the line that cut through the center of both of these charges, basically lie along the line of the dipole, and then we're looking for another point which is directly in the middle of the two charges, but vertically off by a little bit. We can make use of a lot of symmetries, and basically we don't have to use a lot of the tools for handling vectors that we developed before. If we think back, and actually maybe I can put this on screen. If we think back to it would have been video number 2, where we started to look at some of these electric forces on these charges. We kind of did two problems toward the end of the video. We did 21.4, and then we followed it up with a sort of 2D example where we had to use vectors. So I'm going to put it up on screen here just very quickly if I can. I think this should work. Right. So if we take a look here, we can see that we first did this example, right? We did this example 21.4, where we could make use of all these symmetries, and we didn't really have to use a full-blown vector analysis to be able to get to our answer. We were able to argue away that, you know, the upward sort of force experienced will be equal to the downward force, and all we really need to calculate is the x part, and we know it's going to point in the positive I-hat direction, and so forth. And then later on, we did this other problem here, where we couldn't really use any symmetries, and we had to argue. Well, we didn't have to argue away anything. We basically had to do the full-blown vector problem, and we had to do all this sort of vector addition and finding r, and then the magnitude of r, and then r hat, and so forth, and kind of did all that calculation. So this and let me just slide this back over here. This calculation that we're going to be doing here is very much like the first one that we did before, where we can use a lot of these symmetries and we don't have to do the full-blown sort of vector analysis here. And that's kind of why this one's kind of nice and simple as an example for us to look at. Okay, so I won't really be able to have the diagram on screen as I write the solution, since they're on separate pages here. But let me sort of get right into it. So the first thing that we're going to want to do is we remember that we can write the electric field as the electric force over our test charge, right? And then we can also write it sort of in a more useful form for us right now as K times Q over R squared in the direction of our hat, right? But again, as I said, because of the symmetries in this problem, we can sort of pick off the directions that all of these vectors are going to be pointing. So really all we need to do is calculate the magnitude at these points, and then just make some sort of logical deductions, and we'll be able to talk about the sort of directions in which they're pointing. But we still do need to do this calculation of the magnitude, so we need to calculate this basically. Okay, and so we're going to need to calculate the contribution from we're going to need to calculate the contribution from each of these two source charges at each of the three test points that we're interested in looking at, right? So we need to calculate basically 6 different values here. We need to calculate contribution 1 and 2 at A, B, and C. Okay. And so how are we going to do that? Well, really, it's just a matter of simple substitution, right? So we're going to see that I'll maybe do the first one in full detail, and then just copy the answers down from the example of the text. Basically, well, what we end up having is so the electric field from 1, like from source charge 1 at point A, is going to be equal to K magnitude Q1 over R1A squared, right? And so R1A is a distance from 1 to A, right? Written in this way. And so we end up with, well, we can just substitute in numbers. We end up with 9 times 10 to the 9 for our k here. We're told that our charge is 12 times 10 to the minus 9, so 12 nanocoulombs. And our distance here, our r, is 6 centimeters, but we need it in terms of meters, so 0.06 squared. And if we do that calculation, we end up finding that this is going to be 3 times 10 to the 4 newtons per coulomb. Okay, and so this is E1A. We would do exactly the same thing, just find the distance between the source charge and whatever field point we're trying to test for. Write down the charge of our source point, and then just do this calculation over 5 more times, right? So what we would end up finding is that E1B would be equal to 6.8 times 10 to the 4 newtons per coulomb. We would find E1C is equal to 6.39 times 10 to the 3 newtons per coulomb. And then we could also do the same for source charge number 2. We would find that E2A is equal to 6.8 times 10 to the 4 newtons per coulomb. And again, these are all going to come out positive, right, because we are taking the absolute value of our charge here, and that's fine because we can deduce the direction from our discussion that's going to follow after we have all these magnitudes, right? So let me finish off these magnitudes. We'd end up with an E2B 0.55 times 10 to the 4 newtons per coulomb, and finally E2C equal to, well, so E2C, I mean, we can look at the symmetry of the problem here, and the textbook does this as well. We can look at the symmetry of the problem, and we can see that E2C would have to be the same as E1C, because we're not paying attention to the sign of the charge, and it's exactly the same distance from 1 to C as it is from 2 to C, right? So we know that E2C has to be equal to E1C, and that was equal to 6.39 times 10 to the 3 newtons per coulomb. Okay? And now we just need to sort of put it together and write down the vector version of our electric field at these different points. And so we can start off with point A. So if we look at point A, and they've already drawn these in for us, so that's kind of nice. We can see that at point A, we're going to be experiencing a repulsive force from Q1, right? So we expect our contribution from Q1 to be pointing in the right direction, so in the positive I hat direction. And we're going to be experiencing an attractive force from Q2, and so again we expect the contribution from Q2 to be in the positive I hat direction, right? So both of them are working constructively to give us an electric field pointing in the positive I hat direction at A. And so if we know that, we can write down that E at A, the vector, is going to be equal to E1A I hat, right? And that's positive. We just talked about why. And E2A I hat will also be positive. So we can just substitute in numbers. And if we do that, we're going to find that that the electric field at point A is going to be 9.8 times 10 to the 4. This is basically just adding E1A and E2A together here, right? So just adding the two of those together, and that's going to be pointing in the positive I hat direction, newtons per coulomb. Okay. For point B, let's take a look at point B. We can see that our contribution from point 1, from Q1 here, is going to be repulsive. So we are going to be pointing in the negative I hat direction for our contribution from Q1. But our contribution from Q2 is going to point in the positive, right? It's going to be attractive, so we're going to be tending to want to go that way if it was only Q2 acting on us here. So we're going to have Q1 going in the negative I hat direction and Q2 going in the positive I hat direction. So let's do that. We have E and B and we said that E1, so E1b, is going to point in the negative I hat direction, and E2b is going to be pointing in the positive I hat direction, right? And so I'm going to pull out that negative sign. I'm going to rewrite this one more time. So basically, we're going to end up with minus E1b plus E2b in the I hat direction. And if we substituted numbers for that, E1b and E2b from above, we end up with minus 6.2 times 10 to the 4 I hat newtons per coulomb. Okay. And now we only have 1 point left that we need to work with. We need to work with EC. But EC is not quite that simple, right? Because it doesn't lie on the line of the dipole here, right? It lies off the line. It's up here in the j hat direction. And so we can see what our contributions will be like. They kind of drew them on here, so we can see that we're going to have a repulsive force coming from Q1 pointing us up along this line here, and we're going to have an attractive force from Q2 drawing us down on this line here. We can see that the vertical components are going to cancel out here, and we're only going to be left with an EC pointing in the positive I hat direction. The problem here is that we don't know what the magnitude of that EC is, right? But we can kind of get to it. We can see that we have these sort of similar triangles being formed, and so if this angle in here is alpha, it must be true that this angle over here is alpha, right? So we're going to need to find what alpha is, and in fact we don't really need to find what alpha is, we need to find what the cosine of alpha is, right? Because why is that? Because what we have here is we have our, let's say we take the vector that we have drawn up here, which is going to be E1c, right? So if this is E1c, the vector, right? We want to tease out the x component of this. We know that the y components are going to cancel between EC1 or E1c and E2c, but we need to find that x component. So we want to pull out this x component, which I'm going to call E1cx, right? And if this is alpha, we know that E1cx is simply going to be equal to well, I mean, we can also say that E1cx is equal to E2cx, right? Like, we know that the x contributions will be the same for both of these because of our symmetry again. But we can also say that this is going to be equal to the magnitude E1c times the cosine of alpha, right? Because we know that the cosine of alpha is going to pull out that x component here. Or if we wanted the y component, right, if we wanted this y component here, and I could label this E1cy, which we don't want here, but if we wanted that, we know that would be E1c sine alpha, right? But what we need is E1c cos alpha, so we do need this cos alpha. How do we get cos alpha? Well, we just look at the triangle formed below it here, right? We know that this length over here is 10 centimeters, so half of it is going to bring us right to where C is, because we're right in the midpoint here. So we basically have a triangle that looks like this. We basically have a triangle that looks like this. This is a right angle here. This is our angle alpha. We know that this is 5 centimeters long, and we know that this is 13 centimeters long. But since we know that the cosine of alpha has to be equal to, well, from our little mnemonic here, this is how I remember it. We know that the cosine of alpha has to be equal to our adjacent side over our hypotenuse, right? So this has to be 5 over 13. And cos of alpha is exactly what we need, so we can just plop that in here. So this is just going to be E1c 5/13, right? And so we're kind of getting to the end here. Basically what we want is we want EC, the vector, and we know that this is going to be equal to, well, we know it's going to be equal to some magnitude pointing in the I hat direction. We already talked about that. But we know there's going to be twice this contribution, right? Because there's going to be a contribution from E1c and one from E2c, right? So we're going to end up with 2 E1c, because we know they're the same, times 5/13 in the I hat direction. And if you do that calculation, you will end up with 4.9 times 10 to the 3 I hat newtons per coulomb. Okay? And that's the electric field at point C. So we could easily imagine how this problem could be, well, I mean, I guess it depends. This way of doing the problem where we're using these symmetries kind of requires a little bit more sort of thinking outside the box, but you can get to the answer more quickly, right? We didn't have to deal with a whole bunch of vectors, but we could see how we could easily modify this problem and end up with a problem where we couldn't use all these symmetries, much like we saw in the well, 2 videos ago, where we had to do sort of the first problem and then the second one with all the vectors. We could simply adjust this so that these points that we're looking for aren't so nicely on the line, and then we'd actually have to find all these position vectors and actually do the calculation, right? And that's maybe something that I'll do in one of our problem sessions, or maybe save it for an assignment. We'll see in the future. Okay, so that was the one example that I'm going to do for still discrete points, right, where we still have some number of point charges that we're trying to calculate the electric field around. Before we move on, I'm going to make a quick note on notation here. So we're going to write the electric field in a few different ways as we keep working with it, but we kind of have to remember that all of these are in some ways equivalent, right? So we end up with, so if I write the electric field this way, we know the electric field is a vector, so we know it's going to be written in terms of well, I and j hat if we're only in 2 dimensions, or k hat included if we're looking in 3 dimensions, and there's going to be some sort of scalar component out front of each of those unit vectors, right? But each of these is really, well, I mean, E itself is a vector field that varies from point to point, right? And so we could easily attach an argument to our electric field here, and then each of these components would also vary from point to point, right? So written out in sort of longhand, this is what our electric field might look like. Or if we wanted to write it more compactly, just using our position vectors, we could do the same, right? So there's just 3 ways that we should be comfortable sort of seeing the electric field written. Okay, so now we're going to start just setting up the machinery we're going to need to use to be able to calculate these sort of continuous charge distributions. And what I mean continuous, so discrete meaning, well, basically discrete versus continuous. When I say discrete, I mean we have some countable number of points that make up our charge distribution. So we could be talking about one point charge, or 5 point charges, or 80 point charges. Whichever of those, we could sort of go through and add up all the point charges and calculate what the electric field is at some point around that collection of point charges, right? But if we're dealing with macroscopic objects, charged rods, charged rings, or whatever, then we can't really do that. We need to sort of introduce this idea of a charge density, right? So let's say we're talking about a charged rod, for example here. For our first example, I've kind of drawn them out here. If we're dealing with a charged rod, we're going to need to know what the charge per unit length is, right? So this rod's going to have some length, and we need to know what the charge per unit length of that rod is. If we're dealing with a 2D object, or some object we can easily approximate in 2 dimensions, say this square or rectangular sheet that I have drawn here, then we're going to need to know what the charge density in 2 dimensions is. We're going to need to know what the charge per unit area is. Or, again, in 3 dimensions, I tried to draw a sphere here. In 3 dimensions, we would need to know what the charge per unit volume is, right? And so we've kind of reserved these 3 symbols. So we have a lambda, we have a sigma, and we have a rho. And those are the symbols that we're going to use to signify linear charge density, a surface charge density, or a volume charge density when we're dealing with these sort of macroscopic objects, right? And so in principle, or I mean, not even in principle, generally speaking, these three different charge densities could be functions of position, right? They don't have to be uniform. So in general, we would find that lambda would change depending on where on the rod we were, and so we would have a lambda that is a function of position, right? And those types of distributions would be called non-uniform or inhomogeneous charge distributions, right? So they would have charge densities that are not constant over the entire length, area, or volume of the object, right? But we're going to start off by dealing with uniform charge distributions, which are homogeneous, and so they're going to have well, I guess depending on which one we're doing, but they're going to have either linear charge densities, which are constant, or surface charge densities, which are constant, or volume charge densities, which are constant, and then we may amp it up as we move forward, right? So that's one tool that we're going to need when we move on to looking at these continuous charge distributions. The other tool is where things maybe get a little bit complicated. So this is kind of where things get a little bit tricky in the course, because many different students will come in with different backgrounds, right? There are all kinds of people that take this course. There are people who are doing other sciences that aren't necessarily sort of heavily math driven, that are required to do this course. There are people that are going on in physics that are doing this course. There are people that are well into their math degrees that are doing this course. So people's sort of comfort with integral calculus is very different, you know, from student to student in this course. So I'm going to do a very, very quick sort of review of a little bit of integral calculus here. Maybe you're already very, very comfortable with this stuff. You can just skip over this. Maybe you're doing it in your calculus class right now, like many people will be doing Math 112, and you'll probably have just seen this week. And you know, so you guys can use it depending on how you need. But I'll give it a sort of spin from a physicist's perspective as we go through this, and hopefully you guys find this useful. Okay, so the sort of review here, right? So what are we kind of doing? We're going to be looking at integral calculus here and sort of how we need. So I'm not going to go into doing a full review of integral calculus. I'm just going to hit on a couple of key things that we need to address some of these problems that we're going to be coming up against here in the next couple of examples, basically. So what are we looking at? We're looking at a function here. So we have our coordinate system put down. I have some function mapped out here. We're going to call this f of x, and we're interested in finding the area under the curve, right? So this is the sort of canonical problem that we're trying to deal with in integral calculus. We're trying to find this area under the curve. And so I'm going to come back and sort of refer to this diagram as we move on, but I'm going to write down some stuff below. I haven't typed out any notes. I wanted to leave it sort of freehand so we can kind of just go with it as we go. Okay, so let's say we were interested in finding the area under this curve from some point A to some point B along this curve, right? So we have x equals A and then x equals B, and we want to find the area under the curve for that interval, right? So if we want to do this very approximately, we could just sort of break it up into a bunch of large sort of rectangular sections. So basically we're kind of breaking it up into a rectangle that extends from x equals from x equals A here to x1, then from x1 to x2, and we break it up into some number of rectangles. If we break it up into some finite number of rectangles, we get an approximate area, right? So I'm going to write this out. So we could get some approximate area. We could get some approximate area that would look something like this. This would be the approximate area. We would get some A1 plus A2 plus, you know, out to some AN, right? And so our approximate area would look something like this. We would have an approximate area that looks like the sum as I goes from 1 to n f of xi, and I'm going to label these xi star for a reason here, and let's talk about what these terms are. So this xi star would be some midpoint between x0 and x1, where we would pull out the function's value at that point, right? So we have all these different xi that we're going through, xi, well, x1 star, x2 star, and however many we have, and this delta x is the width of the rectangular boxes that we're using, right? So we have this delta x. We're using some width that we're going to keep constant as we keep moving along from A to B, right? But let's say we didn't want an approximate area. Let's say we really want it to be really good about this. Like, we can see that this is already going to be pretty good, right? We can see that we're undercounting in this region here, but we're overcounting in this region here. And for smooth functions, this tends to work out, not too badly. We can see here that we're missing this area, but we're getting a little extra area here, and so forth. And so it's not too bad, right? If we oh, there we go. If we wanted to do better, though, we could find the exact area. So let's write that down. We could find the exact area if we wanted to by taking the limit as n goes to infinity in basically our previous expression here. So we're going to find that if we take the limit as n goes to infinity of the sum as I goes from 1 to n, and as we said, n is going to infinity, of f xi star delta x, this will end up giving us an exact result. So sort of what's going on here? Well, the first thing that we should probably mention is that these delta x's, as n goes to infinity, it must be true that delta x gets small, right? So the more and more of these rectangles we're jamming into this finite area. I mean, we're still only going from A to B, right? So if we increase the number of rectangles we're jamming in there, the rectangles have to get smaller and smaller. So we're getting thinner and thinner and thinner slices, and we're basically overlapping sort of less and less, and we're getting closer and closer and closer to the exact answer, right? This is sort of Riemann sum that we can rewrite, and this is really where the sort of essence of integral calculus comes from. We can rewrite this sum in the limit as n goes to infinity as the definite integral from a to b of f of x dx, right? And so what sort of happened here? Well, I'm not going to go into all the sort of background detail, but basically we can rewrite this infinite sum as this integral here. So this is what's called, or this is what I will refer to as a definite integral. Okay. And so this is sort of what we're going to be trying to get at. We want to be able to, and if you're taking any one skill from your 112 class that you really want to be able to use here, it's being able to evaluate these types of integrals. And there's a whole bunch of tools that you guys are going to learn in 112 if you haven't learned them yet, or you'll remember as we go through them here. But you're going to need to be able to evaluate a number of these different integrals as they come up. So now, for large, okay, so maybe I'll write this out. Oops, and that's terrible. Well, whatever. For large n, we can see that this term, this f of xi star times delta x, is really becoming an area, right? Which I'm going to write as dA. So as we increase n, as n is going to infinity, and these slices are getting thinner and thinner, we're really getting a tiny slice of area, and I'm going to call that dA, under this curve, right? And so in physics, we sort of make this this sort of, or let me finish making notes here. Okay, so we have the infinitesimal area of a rectangle. This is this dA, right? And so in physics, oh boy, I made a mess of this. Okay, so in physics, we write that the area is going to be equal to the integral of all of these tiny infinitesimal chunks of area, right? So we have, do I have space here? I do. So we're going to write that the area is going to be equal to the sum of all of these infinitesimal little slices of area, right? And this is a very useful tool. We're going to see this come up over and over again in physics if we're going on, or even within this course, we're going to see this coming up over and over again. And if we bring it back to the problem of the electric field, what we're going to use here is that we're going to end up seeing that we're going to find that our total electric field, so this will be our total, okay, we're going to see that our total electric field is equal to the sort of integral, or we can think of this as a sum, of all of the tiny little infinitesimal chunks of electric field contribution that we get from the object that we're looking at. So I mean, we're going to look at some examples of this to make it more concrete as we go on. Let me finish making this note here. Okay, so those are our infinitesimal contributions to an electric field, right? So how does this work out? I'm going to go into this in much more detail as we do the actual examples, but let's imagine we had some I don't know, a rod here, let's say, for example. So we had a rod, and there's a charge distribution here, right? There's a bunch of charge on this rod, and so we would have some lambda from it. What we're going to end up doing, let's say we were interested in actually this is the problem that we are going to do. So we're interested in some point P out here, what the electric field is here. So really simply, the sort of breakdown of what we're going to do is we're going to start looking at tiny little slices of this, and each of these is going to have some small contribution. Each little slice of this, each little infinitesimal area is going to have some tiny little contribution, some dE, to the full electric field experienced out here. So we're just going to add up all these little contributions and find our electric field out at that point. And this is basically, this idea is basically what we're saying here. And we're going to spend the next video and maybe longer sort of looking at some examples at how we kind of do this practically. Okay, so I'll see you guys in the next one, where we're going to be pretty much just doing examples of finding the electric field outside of continuous charge distributions.